Good morning, students. Last class we have seen generation of the rotating magnetic field. Now this class we are going to discuss regarding the construction of the three-phase induction motors. Construction of the three-phase induction motor. Construction of three-phase induction motor. Three-phase induction motor is a AC motor, AC motor, AC motor. Induction motor converts electrical energy to mechanical energy. Three-phase induction motor is a AC motor which converts electrical energy to mechanical energy. So let us see what are the main parts of the three-phase induction motor. Three-phase induction motor having two main parts. First one is the stator. This is a stationary part. Stationary parts. Second one is the rotor. This is rotating parts. Rotating part. These two are the main parts of the three-phase induction motor. So first let us see the stators. We will discuss regarding the stator. Stator. Now the stator is a hollow cylindrical structure made up of silicon steel lamination to reduce the losses. So it looks like stator having number of slots, number of slots, slots. These are the slots. These are the slots. This is stator. The stator have a number of slots. These all are the slots. These all are the slots. The stator has slots on this inner surface where insulation, copper, conductors are placed in these slots. Now in these slots, conductors are placed. In these slots, conductors are placed. These conductors may be star or delta connected systems. When three-phase AC power supply is connected to the winding, this winding, then if you three-phase supply is connected to the stator winding, then rotating magnetic field will produce in the stators. Already last class we have seen how to produce the, what is the condition to produce the rotating magnetic field. So as per the principal operation of the rotating magnetic field, if you give the three-phase supply for the these three-phase windings, already these windings are spaced apart from the 120 degrees. If you give the three-phase balance supply, then rotating magnetic field will produce in the stator. This rotating magnetic field will rotate in the area. Rotate in the, these are the rotating magnetic field will rotate in the area. So this is the stator is a stationary device. Stationary device. There is no rotating parts in the stator. Purpose of the stator is to produce the rotating magnetic field, to generate the rotating magnetic field. Next one is the rotor. Next second part is the rotor. A rotor is a rotating parts. The rotor is placed inside the stator and rotates due to the rotating magnetic field. So as per the rotor construction, three-phase induction motors are classified as squirrel cage induction motor and slip ring induction motors. This classification based on the rotor construction. So we are having the two types of rotors. One is the squirrel cage rotor, next one is the slip ring rotors. The slip ring rotors also called the wound rotors. So we will discuss one by one. First let us see the squirrel cage rotor. Squirrel cage rotor. This rotor looks like is the copper bars, but this is the end rings. This is the end rings. So this is the copper bar. This winding is the copper bar. This is the end rings. These circles are the end rings. These copper bars are made up of copper or aluminum conductors placed inside of the steel laminated slots. Both ends of these bars are short circuited two copper end rings, making it closed path. So each winding, each bars are the short circuited in the end rings. So this is a copper bar 1. This is the one more copper bars. All copper bars are short circuited in the end rings. See, this is the copper bar. This is the short circuited. Each bars are short circuited in the end rings. These circuits are the end rings. This is the construction of the squirrel cage induction rotor. This squirrel cage induction rotor having the low starting torque, rugged construction, maintenance is free. This squirrel cage induction motor used in the drilling machines, irrigation pumps, lathe machines, and industrial applications. So next, let us see the slip ring rotor. Slip ring rotor is also called the wound rotors. Second one is the rotor construction is the slip ring rotor, or also called the wound rotor. The wound rotor. This is R, this is the Y, this is the B pace, R pace, Y pace, B pace. This is connected to, rotor is connected to shaft, connected to shaft, connected to shaft. So these rotor conductors are connected to external resistance through the slip rings. Slip ring 1, 2, slip ring 3. These are the brushes. These are the brushes. These are the brushes. Now this is the slip ring. This is the slip ring. Now this R pace is connected to first slip ring. Y pace is connected to second slip ring. Now B pace is connected to third slip ring. Now this RYB, these three rotor windings connected to external resistance, that is, this is the external resistance, external resistance through the slip rings. This is the external resistance. These are the external resistance. These are the external resistance. This external resistance is connected to the rotor conductors, R pace, Y pace, B pace. These are star connected rotor conductors connected to external resistance through the slip rings. Through the slip rings. These three are the slip rings. These three are the slip rings. This is the construction of the slip ring induction motor. So what is the main advantage of the slip ring induction motors compared to squirrel cage induction motors? This is used for the where high starting torque is required. Where high starting torque is required, at the time we have to prefer the slip ring induction motors. Why? Because starting torque T suffix ST. The starting torque, T is the torque, ST the starting torque is directly proportional to rotor resistance. R suffix 2 means rotor resistance. Now this is the rotor, this is the rotor having resistance. Now starting torque depends upon the direct proportional to rotor resistance. So by adding some rotor resistance to the rotor conductors, is the rotor resistance adding to rotor conductors. Now total resistance will be increases. Total resistance will be increase. Whenever total resistance, rotor resistance will increase, starting torque also increases. Where high starting torque is required, at the time we have to prefer the slip ring induction motors. Here the slip ring induction motors windings are the star connected winding. Carbon brushes rest on these rings allow the external resistance. These are the carbon brushes. This external resistance is connected to slip rings through the carbon brushes. Applications of the slip ring induction motors are used in the elevators, conveys, traction systems, and where high starting torque is required. Where high starting torque is required, we will prefer the slip ring induction motors. This is the construction of the three-phase induction motors. Construction of the three-phase induction motors having two main parts. One is the stator and rotor. Based on the rotor construction, these induction motors are classified as squirrel cage induction motor and slip ring induction motors. These two classifications based on the rotor constructions. This is the construction of the three-phase induction motor. Now, next let us see the working principle of the three-phase induction motors. Working principle of the three-phase induction motor. Three-phase induction motors. Working principle of three-phase induction motors. The three-phase induction motor works based on the Faraday's laws of the electromagnetic inductions. So, principle of the three-phase induction motor, Faraday's laws of the electromagnetic induction. What is the principle? What is the meaning of principle? How induction motor is starting? In the induction motor, two main parts just now we have seen. One is the stator, one is the rotor. How rotor is starting? How rotor is pick up the speed? That is the principle. So we will see the how motor is going to start in the induction motors. We have seen two main parts of the three-phase induction motor. One is the stator, one is the rotor. Let us see again. Stator. This is the stator. The stator having stator conductors or stator windings. This is the stator conductors. Stator. This is the stator conductors. Stator conductors. This is the rotor. Inside of the stator, rotor is placed. This is the rotor conductors. This is the rotor conductors. Rotor conductors. Now this is the stator conductor. Now this is the rotor. This is the rotor conductors. Or rotor conductors are rotor conductor bars. Rotor bars. Now outer part is the stator. Inner part is the rotor. Stator having stator conductors. Rotor also having the rotor conductors. So here this is the stator. This is the totally the stator. This is the rotor. Between these two, some gap is there. This gap is called the air gap. This gap is called the air gap. To rotate the rotor freely, we are maintaining some gap between stator and rotor. This gap is called the air gap. This is the rotor. This is the rotor. Between these two, some gap is there. That is the air gap. If you give the three-phase supply for this stator winding, if you give the three-phase supply for the stator winding is the R phase, Y phase, B phase. If you give the three-phase supply for the stator winding, as per the uh, principle of the rotating magnetic field concept, already you have seen, rotating magnetic field will produce that rotating magnetic field will rotate in the air gap. This is the air gap. This is the air gap. In this air gap, rotating magnetic field will be rotate. These are the RMF, rotating magnetic field will produce in the stator winding. This rotating magnetic field will rotate in the air gap. Rotate in the air gap. This is the rotating magnetic field. The rotating magnetic field. Then what will happen? This rotating magnetic field speed is this rotating magnetic field will rotate speed with the ns is equal to 120 into f by p. This rotating magnetic field speed is represented by ns. That is called the synchronous speeds. That is the synchronous speed. This rotating magnetic field speed is 120 f by p. Is the f is the supply frequency. Now p is the number of poles on the stator. So synchronous speed, rotating magnetic field speed is the synchronous speed, that is depends upon the 120 f by p and f. So this rotating magnetic field, whatever may be producing in the stator winding, stator conductors will rotate with this speed. Now rotor is the standstill projections. There is no movement in the rotor at the starting. Rotating magnetic fields are produced and rotating with these speeds. Rotating with the speed. Now rotor is the zero speeds. Now n suffix r is the zero speed initially. Now rotating magnetic field is rotating with the synchronous speed. RMF, rotating magnetic field speed is the ns. Rotor speed is the zero at the starting. See, at the time of starting, rotating magnetic field speed is the synchronous speed, rotor speed is the zero. As per the Faraday's laws of electromagnetic induction, to produce the EMF, required thing is the flux is required, conductor is required, and relative speed is required. Now here conductor is the rotor conductors. Now conductor is the rotor bars. Now flux is the rotating magnetic field. Now relative speed is the rotating magnetic field is rotating is with the synchronous speed. Conductor is the stationary. Now rotating magnetic field rotating is the synchronous speed. So between these two, between flux and rotor conductor, relative speed is there. So as per the Faraday's laws of electromagnetic induction, EMF will produce in the rotor conductors. EMF will produce in these rotor conductors. As per the Faraday's law, flux, conductor and relative speed, these three are there, automatically EMF will produce in the rotor conductors. Now these rotor conductors are already short circuited in the end rings. So current also flowing through these rotor conductors. Whenever current is flowing through the conductors, flux will be produced. So here two fluxes are there. One is the rotating magnetic field flux, one is the rotor flux. So whenever current is flowing the rotor conductors, means that is the current carrying conductors. Current is flowing through the rotor conductor means current carrying conductors. As per the motor principles, current carrying conductor placed in a magnetic field, a mechanical force is developed on the conductors. So whenever EMF will produce in the rotor conductors, these rotor conductors are the short circuited in the end rings. So current also flowing through the rotor conductors. Now these conductors are the current carrying conductor placed in a rotating magnetic fields placed in a magnetic field. A mechanical force is developed on the conductors. So at the time torque is produced on the conductor, due to the torque, this rotor start to rotate. Start to rotate. If you see, this is the north pole, this is the south pole. North pole and south pole. Now flux is flowing from north pole to south pole. This is the, in our concept, is the rotating magnetic field. This is the rotating magnetic field. This is the, this arrow marks are the rotating magnetic field. This is the flux produced by stator conductors. Now rotor is placed in the between the inside of the stators. Inside of the stator. Here rotor is there. Here rotor is there. This rotor will, in the rotor bars, as per the Faraday's laws of electromagnetic, EMF will produce. Due to that EMF, current will flow. Again, flux will be produced. This is the rotor. Here, flux produced in the rotor is the like this. Be like this. Now see here. This is already flux one. Already the flux one means rotating magnetic field. When your current is flowing the rotor conductors, again flux will be, one more flux will be produced. This is the second flux. This is the second flux. If you see the second flux direction, now this is the north pole and south pole. This is the rotating magnetic field. Rotating magnetic field. Rotating magnetic field, RMF. RMF. Now this is the rotor. Rotor is placed inside of the stator. Now whenever current is flowing the rotor conductor, second flux will be produced. This is the rotor flux. This is the rotor flux. If you see the rotor flux direction, now see, this is the flux direction. You can assume like this. The clockwise direction. This is the clockwise direction. If you see this rotating magnetic field flux direction, this is the rotor flux direction. This is the phi r, this is the phi f. Phi f is the rotating magnetic field, phi r is the rotor flux. Phi r is the rotor flux. If you see right side of this rotor, now rotating magnetic field flux and rotor flux, both are the same direction. Both are the same direction. If you see left side of this rotor, rotating magnetic field direction is the downwards, rotor flux direction the upwards. This is the opposite direction. This is the opposite direction. These two are the same directions. These two flux are the same direction. The right side, this side is the opposite direction. So resultant flux will be, here will be going to added. Here total flux is the phi f plus, as per the magnetic field properties, two flux are the same direction. Two flux are the same direction. Here total flux is equal, two flux direction is same. So phi f rotating magnetic field plus phi r, both total flux will be added. Total flux will be added, then total flux is going to increase. Total flux is going to increase. Now left side of this rotor, now rotating magnetic field flux direction is downward, now rotor flux is the upward. So here total flux is the resultant of the rotating magnetic field and rotor conductors. Now this is the subtracted. Now resultant flux is the rotating magnetic field minus rotor flux. Now this side is the both flux will be added. This side is both flux will be subtracted. So this side flux will be strong. This side flux will be weak. This is the strong magnetic field. This is the weak magnetic field. At the time, this conductor will move from strong magnetic field to weak magnetic fields. This is the strong magnetic field this side. This is the weak magnetic field. Now, conductor will move from strong field to weak field. That movement is the force. That is the torque. Now, like this, a rotor is start to rotate in the, then this conductor, this rotor is start to rotate in the air gap. Rotate in the air gap. This is the principle of the three-phase induction motor. So induction motor is a self-starting motors. 3-phase induction motor is a self-starting motors. As per the Faraday's laws of electromagnetic induction, two fluxes will be produced. Two fluxes will be produced. Interaction of these two fluxes, torque is produced in the rotors. Due to the torque, the rotor continuously starts to rotate, continuously rotating. Now this rotor try to get the rotating magnetic field speeds. Try to catch the rotating magnetic field speed, but that is not possible. If a rotor will run with the rotating magnetic field speed, there is no relative speed between flux and conductor. Then relative speed is zero, EMF also zero. Relative speed is zero, then EMF also zero, then current also zero, then torque also zero. So all will be zero. If you rotor will rotate with the same rotating magnetic field speed, then relative speed is zero. Whenever relative speed is zero, EMF also zero, current also zero, torque also zero. That's why always rotor will run less than the synchronous speeds, less than the rotating magnetic speeds. So this is the principal operation of the 3-phase induction motors. Thank you.